Computer vision seeks to infer a wide range of information about objects and events. However, vision systems based on conventional imaging are limited to extracting information only from the visible surfaces of seen objects. For instance, a vision system can detect and identify a Coke can in the scene, but it cannot determine whether the can is full or empty. In this work, we tackle the problem of inferring liquid fill levels inside opaque containers remotely without any physical interaction or weighing. We achieve this by sensing the tiny vibrations induced on the container by a nearby speaker and relating them to the container's liquid level. To infer the hidden liquid level, we must overcome two major challenges. First, the container vibrations are too small and too fast to sense using a conventional camera. To capture these vibrations, we introduce a novel speckle-based imaging system capable of capturing the tiny surface vibrations at multiple object points for multiple containers at once. The second challenge is relating the captured vibrations to the hidden liquid level. In general, the vibrational response of an object depends on the object's stiffness, density, geometry, and for liquid container, the amount of liquid inside. Take a wine glass as an example. This glass has a single dominant resonance tone that shifts lower in frequency as the glass gets filled. Unfortunately, such a simple relation does not apply to most everyday containers. For instance, tapping an off-the-shelf milk carton at different fill levels creates different sound responses. But these responses do not have a single dominant mode like the wine glass, making the liquid level inference a challenging task. This complex response relates to the spatially varying vibration modes excited on the container surface. Therefore, sensing multiple surface points helps yielding more reliable liquid level prediction. To test our approach, we use our novel imaging system to capture a dataset of various everyday containers for multiple liquid levels while exciting their vibrations using speakers at different spatial locations playing various audio files. Next, we explain how we use the captured data to learn how to extract a container's liquid level. Our camera captures the speckle interference of all the surface points at once. For each surface point, we extract two axis vibration signals from the video region of interest belonging to that point. The raw vibration signals are processed by a novel vibration transformer architecture. The vibration signals are then converted into Fourier domain magnitudes, which are then tokenized into separate frequency bands and embedded with the band's position in a predefined frequency range. Next, these tokens are inputted into a shared point transformer which analyzes the local frequency spectrum at each surface point. The aggregate token from each point transformer is then fed into a shape transformer which fuses information from different surface points, yielding a final aggregate token which is used to infer the container type and liquid level. During training, we minimize a joint loss consisting of a soft ordinal loss for the liquid level prediction and a cross-entropy loss for the container classification. We tested our model's liquid level prediction in 4 validation categories. The first category is containers from our dataset, but with a new and unseen speaker positions. In this test, the mean absolute error for the fill level prediction was only 1%. The second category is new unseen containers whose type exists in our dataset. We also tested the prediction of fill levels that lie in between the levels in our training set. The sword loss component of our loss function helps us to yield reasonable predictions in this category, even though the model had never seen the in-between levels during training. Finally, we tested the model using simulated ambient background noise instead of playing a chirp or a song segment. The model still performs well, suggesting that operating in the frequency domain makes your system mostly invariant to the input stimulus. Our approach was inspired by many relevant prior works, including fast speckle-based vibration sensing, vibration-based material analysis, methods for inferring hidden properties, and liquid level estimation. However, our approach is the first to eliminate the need for any physical interaction with the container or reliance on nearby microforms, enabling passive, remote inference of liquid content using only visual measurements. Looking forward, we believe that our method opens the door for a wide range of novel exciting vibration-based computer vision tasks like figuring out the content of closed boxes, detecting spoilage in sealed goods, monitoring agricultural crops, detecting the chemical composition of substances within closed containers, and more. Thank you for listening. Visit our webpage for more results.